Okay, so let's go ahead and cover the last sections of chapter 6 here. We can probably cover them both today, but we'll just see how we're doing. Before we start, I guess, does anybody have any questions that they would like answered from things that you looked at this week? Yeah, from the current chapter.
I'm sure it's a lot more simple than this, but first question.
The first question is from chapter 6, number 1. Okay, so this is actually what we're going to actually cover this stuff today. So let me just go through a few things in the chapter today before I do this for everybody, so that everybody understands what we're doing in this. Anything that follows a circular motion has a slightly different approach to it. So let's cover the circular motion first. Then we'll get back to it. Centripetal force. Now, why they throw this in right here, I don't really know. But they do. It's not until we get into, let's see. I guess they do this earlier. They cover uniform circular motion here in chapter 4. And I don't know why they throw these things in the middle of these different chapters. They should just have their own section for circular motion, but it's just the way they've decided to do it. One of these days I'll have the time to rearrange this book the way I want it, and I'll do that. But in the meantime, we'll just do it the way they do it. So what is centripetal force? Centripetal force is the force that causes things to turn along circular paths. So if something's going around and around a circle, there's a force that is causing it to do that, because if you're turning, you're accelerating because you're changing the direction of your velocity. So that is considered an acceleration. You can even go at you can go at a constant speed around and around a circle, and you're still accelerating. That acceleration is called the centripetal acceleration, and that acceleration is always towards the center of the circle. It points towards the middle of the circle that you're traveling on. And there are a couple of equations that we can learn about this. One of them being we've already learned about this. The centripetal acceleration equals the speed along the edge of the circle squared divided by r. And if you use the conversion between linear speed or tangential speed along the edge of a circle and angular speed, or how much angle you're going through, then centripetal acceleration also equals r times omega squared. So you can calculate the centripetal acceleration fairly quickly, fairly easily, with things that are easy to measure. The centripetal force then is, of course, mass times centripetal acceleration. So the force that causes this thing to accelerate towards the center of the circle is just mass times the centripetal acceleration according to Newton's second law. If we replace the acceleration in this equation with either of these two things, we get two other equations for this: mass times v squared over r, or mass times r times omega squared. So you can calculate that centripetal force fairly easily also. Now, the things that are always true with centripetal force is that your velocity along the edge of the circle, or your instantaneous velocity along the edge of the circle, which is actually a vector, and the centripetal force and also the centripetal acceleration are always going to be perpendicular to each other. So here you have this right angle between the centripetal force and the actual velocity. And that's actually why it doesn't change the speed of the object. It just changes its direction, because there's no force pushing it in the direction that it's moving, so it doesn't change the direction. It doesn't change the speed of it in the direction that it's moving. It only changes the direction. It just pushes it into a different direction. And then, of course, the other thing that is always true is that the centripetal force and the centripetal acceleration are always parallel to each other. They're always pointing in the same direction. But that's true of all forces and accelerations. The net force on any object is always parallel to the acceleration on that object. So here is a car turning a corner. You guys see the front wheels are turned, and that's actually what causes this centripetal force. As the car tries to roll forward, the wheels are turned, and so they push. The tires push against the ground, and the ground pushes back. And as the ground pushes back, it creates that centripetal force, which causes the circular motion. So if you're going to draw a free body diagram of this car, you'd have the weight of the car downward, and the normal force of the car upward, or of the ground upward rather, and then the friction force on the wheels inward, towards the center of the turn. So that's your, this frictional force then becomes your centripetal force, as it's shown here. Centripetal and friction are the same. And in this particular example, they want us to calculate the centripetal force that a 900 kilogram car needs to negotiate this 500 meter radius curve at 25 meters per second. And we're assuming an unbanked curve, so the curve is, you're not going around at some kind of angle. So all of the force that is turning the car is the frictional force. So what we really need to do is calculate the frictional force. But one thing that confuses people is that what kind of friction is this? Static or kinetic? Anyone care to make a guess? Kinetic friction is the guess, okay? Anybody agree with that or disagree with that? Okay, so that we can be right no matter what. It is actually static, but why? Why is it not kinetic if the car is moving? Is it the car that's got friction with the ground? It's the tires. The car is moving. Are the tires moving relative to the ground? Well, it depends on which direction you're looking at the tires, right? If you look at the tires from the front, right, then they're not moving. They don't look like they're moving relative to the ground. Why is that? Because when you look at from the front or from the back, what you're seeing is the side-to-side and the up and down direction. The side-to-side direction of the tires doesn't move. The tires don't move side-to-side. They don't move up and down. If you look at it from the side, of course, the tires are moving. But which direction is the force pushing on the tires? Is it pushing on from the side or from the front or back? Which direction is the friction pushing to turn the car? Imagine this, you're driving down the road and you turn your wheels to the left. Then all of a sudden your car wants to keep going forward, but the wheels turn it to the left. So which way is the car trying to push those tires? Is it trying to make them roll forward, or is it trying to make them slide sideways? It's trying to make them slide sideways, right? And those tires sticking to the ground is what's preventing the car from going straight, or in other words, it's the thing that turns the car. So the sidewards force on the tires, there's no experience, there's no sliding going on there, unless you skid. If you skid, then it's a different thing. But if you turn this without sliding, then you're fine. So in this direction, the tires technically aren't moving. You know, they're not moving left and right. They're just turning left and right, and then that turning causes the friction, which pushes the car. So it is static friction, and they want us to calculate. They want us to calculate the minimum static coefficient of friction between the tires and the new road, and the road, not the new road. But anyway, so what we do is we write down our force, our centripetal force equation. Force centripetal equals mass times v squared over r, where v is the speed around the turn. They've given us all that information, so we can calculate the amount of force that we need to turn the car. This is the amount of frictional force required to turn the car around this curve at this speed, right? If we set that equal to the static friction, which is mu s times n, which is the normal force, remember that on a flat surface where gravity is the only thing pushing the object down, your normal force is going to be equal to your gravitational force, which is your weight, so that's m times g. So now you have your frictional, your centripetal force equal to your frictional force equal to mu s mg. Well, your centripetal force was mv squared over r. So if we solve this equation, the centripetal force equals the frictional force. If we solve this for the static coefficient of friction, look what goes away. The mass of the car goes away. It turns out it doesn't even matter what the mass is. The only thing that matters is the speed of the car, the radius of the turn, and the gravitational constant. So for any given turn, you can calculate what the static coefficient of friction should be between the tires and the road, right? It doesn't matter what the mass is. You just need to put a particular static coefficient. And this is why they can put signs on the road that says this turned 25 miles an hour, right? Because it's the same for all cars. And all cars are designed so that they have a minimum amount of static friction between their wheels and the road. So cars that are heavier have to have a different number of tires, type of tires, than cars that are lighter, right? Because there's a different amount of friction due to that gravitational pull, but the actual speed you need to go around a radius, any particular curve of radius r, is determined just by those things. So it turns out that you want a minimum static coefficient of friction of 0.13, and most tires are quite a bit more than that, because you want to have a little overkill, right? You want to be able to go around turns a little bit better. And if you look in previous section that has the list of things, they have one for tires on a road, and it's better than that. What happens though if you don't have a flat curve? It changes things entirely. In fact, this is a good thing, because what's going to happen is that you're not going to need as much friction between your wheels and the road to go around a curve. And if you've ever been in a big city where they have big highways going between hills and things, you'll see a major bank in the freeways, so that cars can still go at fairly high speeds. They don't have to have super slow traffic and not slide off the road. Of course, they have them on race car tracks as well. But if you have a banked curve like this, what really happens is the normal force changes. Because your weight is straight down like this and your normal force is at this angle, the normal force is no longer going to be equal to the weight of the car. It's actually going to be less than the weight of the car. Okay? And you can actually solve for the normal force. They do this here, solving for the normal. Actually, what they're going to do here is solve for the angle. So we have in this case, we have a car that has a weight W, and then the angle theta is the angle of the road banking right here. And there's a frictional force here that's going to turn the car. So this force that turns the car this way is still pointing off in this direction, that frictional force, and that's fine. And we want that force to be big enough to turn the car around. But there's two things that are going to contribute to this force. The normal force actually has a component. Part of the normal force that's pointing up this way is pointing this way, right? And if you bank this curve enough, then you don't actually need any other force but the normal force. The normal force can do it all if you have it at just the right angle for the particular speed of the car, a particular speed around a particular angle. So in this problem here, they're actually solving for the angle of the road that you need to have for a particular speed around a particular radius, so that you can bank the road perfectly for a particular speed. When they do that, what they've done here is they've got the n sine theta. N sine theta is this inward component of the normal force. So that's n sine theta, where theta is here. It would be up here if you moved it to make the right triangle. So n sine theta is actually equal to the centripetal force. And then they want to make that equal to the centripetal force, of course, mv squared over r. N sine theta, mv squared over r. Well, the n is actually, what is the n equal to? What part of the weight is it equal to? Well, it's this part of the weight if we rotated it down, and this would be theta. And so that would be n times cosine theta, would be that part of the weight that is pointing in the same direction as this. So that's the weight in the parallel or perpendicular direction, essentially. So they end up putting, in place of n, they put n cosine theta. And so now you have n cosine theta, they did this a little bit funny, but that's fine. either way, what they did is a little bit different. They solved n cosine theta equals mg, and then they solve this for n, and then they plug it into here. I did it the other way, but either way, what happens is you replace this n with cosine theta over mg, or mg times cosine mg over cosine theta, or however you want to do it, and you get this equation. Now you get mg times sine theta, so you get the sine theta there, but now you divide by the cosine theta that comes out of this equation. So now you have mg sine theta over cosine theta, which is mg tangent theta. And then you divide both sides by mg, and you get v squared over rg on the right-hand side equals tangent theta. That tells us that if we know velocity, and we know the r, and of course we know g, we can just plug in our velocity, plug in our radius of our turn, and calculate the perfect angle that we need to make that turn so that we don't have to use the friction of our tires at all. So if you bank the turn just right, you can go around that turn and you don't have to do anything. You don't even have to turn your wheels at all. You can just drive straight around it and it'll turn your car for you, right? This is actually how you turn when you're racing cars. When you're racing cars, you want to go into every turn at just the right height and at just the right speed. Because the higher you go up on the turn, you're at a bigger radius from the center of your turn. The lower, you're at a smaller radius. And race car drivers know this. This is how you win races. If you know how to go into a turn and come out of a turn just right, then you won't burn any of your tires up. Your tires won't be worn out. And the worst thing you can do is wear out your tires constantly in a race, because what do you have to do when you wear out your tires? You have to come in, you have to pit stop, you have to change your tires, you lose time, right? You get behind every time you do that. So, so racing is all about conserving tires, conserving fuel, and not having to pit stop. So every turn in a race they calculate, and most of these race teams now actually have an engineer or a physicist on their team whose entire job is to make calculations very quickly during the race. And they usually have several calculations already made before the race, but if that race plan changes, then they have to recalculate, right? So let's say that you're coming into a turn and you have to pass somebody. You're trying to pass the person in front of you, and they're going into turn at one particular height. How are you going to pass them? Well, if you go in at a different height, so your R gets bigger, if you go in higher, then your speed has to be higher, right? So if you go in higher on the turn, then your speed has to be higher, but your distance is also longer. So you got a little bit of a problem there. But if you go in high in the turn and then you come out low on the turn, then you can actually lower your R gets smaller, right? And you can waste a little bit of tires to pass somebody up. So you can take advantage of speed in turns, right? And that's what they do this all the time in racing. They know, they even have calculated how much tire they're going to lose by doing that. They even know how much friction, because what happens when you have the friction against the track is you can slide, and that's one thing that can happen, but the thing that happens most is evaporation of your tires. Your tires get hot, then the rubber evaporates and you lose, width of your tire, thickness of your tire. So anyway, they know exactly how far they can get it down before they have to come in and pit stop. If they go any longer than that, they know they're going to blow a tire. They're going to go through one of their tires and lose air out of their tires. So. Anyway, that equation then comes out like this if you solve it for theta, and now you can calculate the ideal angle for a banked curve. You could also, if they give you the angle, you can calculate the ideal speed through a curve, or the ideal radius for a curve at a different speed, at a particular speed. So you can calculate anything if you want to. That's what they do in this example. The ideal speed to take a steeply banked curve, they just solve it for v instead of for theta, and they plug that in there. Very similar thing happens with airplanes, except it's not friction so much as it is what we call lift. As an airplane, airplanes are kind of funny because they have 3 different ways that they can turn. Okay, so they have their rudder. The rudders use their pedals. The pedals on the floor are the thing that turn the rudder. So you can turn the rudder, and some planes have multiple rudders. But what that does is it actually turns which way the plane is facing, and then your engines can push it in that direction. But that's actually not the safest way to turn a plane. It's not the best way to turn a plane. It gives the plane what you call yaw, what's called yaw, which is rotation along, as you're looking down on the plane, it's rotation of the plane in that dimension. And yaw, if you have too much yaw on your plane, you can actually completely lose control of your plane. You go into what's called a flat spin, and you're almost irrecoverable, and you're going to crash. So you don't want to use your rudder to steer your plane very much. You mostly, in fact, some people will just lock their rudders down and only use them a little bit here and there. But then you have your flaps as well. You have flaps and ailerons. But anyway, what these are on the wings, and they're things that make the wings longer, or they can change the shape of the wing. You can do both of those things. And sometimes they also have them on the back of the plane as well. Depends, those aileron, those are usually called elevators when they're on the back. But anyway, the point is that you have these flaps on your flying surfaces that can be moved as well. What the flaps can do, what you can do with the flaps is you can raise one and lower the other, and that actually banks the plane. That causes lift to go up on one wing and down on the other. It causes force up on one wing and down on the other. And so it causes the plane to bank. And really when you're turning, you use a combination of both. You bank the plane and you turn your rudder just a little bit. And that gives you the perfect turn. And so in this case, they're banking their plane, and they don't actually show the flaps. If they were showing the flaps doing this, then the flaps on this side would be down and the flaps on this side would be up, and you would be turning the plane. But in this case, you have lift. That is, the lift of the plane is upward this way. Total lift on the plane is upward this way. So it has a component in this direction and a component this direction. The component this direction is the component keeping the plane up, right? The component this direction is the component that's turning the plane, right? And then of course you have the weight of the plane downward from gravity. And it's the same idea. It's the same deal with the angles. You can use this equation right here for that. Except in place of, when you're deriving it, in place of using, frictional forces and things like this, you would be using that lift force. But it's the same equation in the end. It's speed and radius, and you're good to go. So now we're going to introduce you to a couple of fictional forces, not frictional, but fictional. We call these pseudo forces. I'm having a hard time teaching two physics classes at once because I teach a little faster in the other class than I do in this one because they don't have as much time. And so it's making me crazy. So we didn't talk about pseudo forces yet, right? So when you're inside of a car and somebody turns the wheel to the left or to the left or to the right or whatever else, you always feel it, right? What do you feel if you're driving along and somebody turns the wheel to the left? What force do you feel in the car? You feel going to the right. But actually that's Newton's first law. How is that Newton's first law? Yeah, the car is turning in front of you and you're trying to keep going, and what do you run into? The door that just turned in front of you, right? So you feel yourself, it feels like you're getting pushed into that door or your seatbelt or whatever, but it's actually you just kind of trying to go straight. I always imagine having one of these, Jeeps that has all the stuff taken off of it, so it has no doors and no seat belts and everything else, and has those slick seats, and you've just been to the beach and you're in a wet swimsuit, and somebody jerks the wheel real hard and you just slide right out of the car and keep going. Right? Wouldn't be a very pleasant experience, but that's kind of what you imagine Newton's first law doing to somebody, and that happens all the time, unfortunately, people who drive without their seatbelts on. But that is Newton's first law. It's just your body keeps going and doing what it's already doing while the car turns, around you. The force that you feel is often called the centrifugal force. You've heard the centrifugal force before thing. And it's not a real force. It is just Newton's first law you're just in a different point of view, from a different point of view, right? However, if that car is completely enclosed and you don't even know you're in a car and your world is that car, you don't know the difference. You don't know that there's not a force that does that. It just randomly shoots you off in some direction. In fact, at the university I went to, and I've toyed around with building one of these, the university I went to, they had two different demonstrations of this. One where they had these spinning dental chairs. And I kind of toyed with the idea of getting one of the dental chairs from downstairs when they trade them out and put a motor on it. But anyway, they put these motors on these spinning dental chairs. So you'd sit in the dental chair and then you had this table that would fold down in front of you and it had a little cover on it up top. And then you do experiments on a table while the chair was spinning. Oh man, it made you sick. And also, the experiments were just wacky. You'd roll a ball straight across the table and it'd go, whoop, you know, it'd turn off. And then they had a room built out of two big taxidermy tubs, which is another, I've had this thought of making one of these too. It was just two taxidermy tubs welded together and a door put in the side and a motor on the bottom. You get inside this room and they turn it on and start you spinning so you couldn't see what was going on outside. There was a light inside and everything else. And then you would do experiments in there. You'd like throw things back and forth. I always thought they should put squirt guns in there. So you could try to have a squirt gun or shoot at somebody and watch the water go off this way or this way or whatever. You can hang pendulums and watch the pendulums go around in circles and weird stuff like that. If you live in an environment like this, you don't know that the outside world is different. And this is the reason that we named the centrifugal force, because we didn't know that it was not a force. Just being in a car was like being in another world. And most people don't even know that. Most people don't realize that it's Newton's first law and not some force that's causing them to run into the door or to lean into the door. And in real life, you know, even outside of cars, we experience this all the time. And we just had an experience of this with the storm season that we've been having this year. So hurricanes are actually caused by a type of pseudo-force, a force that doesn't really exist. You have wind that's traveling along the earth. It's traveling along north, south, east, west, you know, in all kinds of different directions. And the earth is turning underneath those winds. And as the earth turns underneath those winds, we perceive those winds as having experienced a force, right? In reality, they're just doing what they do. And the earth is spinning underneath them, right? So as the earth rotates underneath these things, these storms are created. You have intersection of different winds coming from different directions, and these intersections create these low pressure zones, high pressure zones, all these different pressure zones. Air moves up and air moves down. You have lots of wind and lots of rising water and all this crazy stuff. And these kinds of forces are not as simple as the centrifugal force. The centrifugal force is really simple. This is what we call a Coriolis force, which is more two-dimensional than the centrifugal force. The centrifugal force is more about going in a straight line, something turning off in one direction. The Coriolis force is more two-dimensional and more kind of crazy. And we're not going to do the math of these forces. The math of these forces is way beyond what we can do in this class. It's not impossible to do. It's just a couple of years down the road. If you continue on in engineering or you continue on in physics, and even if you continue, if you went on to study atmospheric sciences, you would study these things as well. You would take the physics classes that you are required to learn about this. But it does require some mathematics that are a little more complicated. So this is the Coriolis force. This is also, incidentally, this is also the force that many people like to blame the turning of toilet water in the toilet. They like to say the toilets in the northern hemisphere turn one way and the southern hemisphere turn the other way. Well, I guess you could blame it on that. It certainly has some effect on that. But anyway, water will definitely tend to go one way rather than the other because of that. Especially big water toilets, I'm not so sure would be affected so much, but anyway. Okay, so is this the last section? It is. And we've got enough time to do it. The last section is about drag force. Now, drag force is just like friction, where it's two things rubbing together, but it's fluids usually rubbing on an object, rather than two objects, two solid objects rubbing against each other. So when an object moves through a fluid, now a fluid can be a liquid or a gas, and that fluid can be, something as benign as water or something as crazy as, seawater full of plankton or something, you know. It can be all kinds of things. But it can be slime. It could be who knows what it could be. It could be all kinds of things. But as things go through a fluid, move through a fluid, they experience a type of friction. And this type of friction, because it goes around the object instead of just being in contact with one side, we treat it differently. The mathematics is quite different. In the end, you can simplify the mathematics down. This is not by any means perfect. None of the equations we work with are perfect, not even Newton's laws. But the drag force can be kind of watered down, so to speak, into this form for very simple situations. 1/2 c times rho being the Greek letter rho, times a v squared. Now, of course, the v is going to be your speed, just like it always is. The lowercase v without any boldface is the speed, it's not the vector velocity. So if you take the speed through the fluid squared, and then the rho is used for the density of the fluid. So whatever the density of the fluid is, you put that there. Density being defined as mass divided by volume. And then the area is the cross-sectional area of the object moving through the fluid. So you have to look at the object as if it's coming at you through the fluid, and then you cut it like that, and you calculate the area, cross-sectional area, right? And then you have this big C thing, which is actually the drag coefficient. Now, the drag coefficient is determined by the fluid, by the shape of the object, not just the cross-sectional area, but the entire shape of the object, by the material of the object, by the temperature of the fluid. It can be all kinds of things. It can be pressure. Lots of things go into that drag coefficient. And that's why this is a very kind of approximate figure. But anyway, this will give us a basic idea for what the drag is. And they have a more generalized version here, v to the n, because this v squared thing is not the whole picture. It's most of the picture, it's not the whole picture. And in fact, this can be generalized even more as a series, or a series, or I think it could be called a series. But anyway, we have multiple terms. So anyway, your drag. This is your drag. And you can actually see the different drag coefficients for different things. These are different things in air. So things moving through air. An airfoil, which is the shape of a wing, has a very low drag coefficient, 0.05. That's why we use that shape for wings, actually. One of the reasons. Toyota Camry, Ford Focus, Honda Civic, Ferrari Testarossa. This was written, obviously, a while ago when the Ferrari Testarossa was a hot car on the market. Then you have a pickup truck, a sphere, right? Notice that a sphere is a fairly large drag coefficient. A big square rectangle, like a big truck or this Hummer, is even bigger, right? It's kind of just a big rectangle. Skydiver, bicycle, a horizontal skydiver, that's the highest one yet, and a circular flat plate, very, very high drag coefficient. And the higher the drag coefficient, of course, the more drag there is. And you can see things that have low drag have interesting shapes to them. Like this is very round, very smooth, but you can see towards the back here there's some tapering going on. Like it's kind of fat in the middle, skinny in the front, tapered in the back. Airplanes are the same way. They're kind of fat in the middle and the front, and then they taper as you go back. Wings are that same way. Here's an interesting one. You have the suits that were used in 2008 Olympics. When they used these suits in the 2008 Olympics, it actually, like world records dropped like flies. And then they immediately banned them. They're like, this is no longer going to be a thing. So now men can only wear suits that I think that go from waist to knee, and women can only wear suits that that have tank tops and go to their knees or just above their knees. And they can't be made of this special material. Right in between, you have these special materials here, and then in between you have these other materials. This actually allowed the water to flow more uniformly around the body, across the body. Swimmers have always known that this was a thing. Swimmers are famous for shaving. So they swim all year long, working out, hair on their bodies. Even women swimmers will actually let the hair on their bodies grow, the hair on their legs and arms and everything else, just kind of grow. And then they'll wear 2 or 3 swimsuits, and then their outside swimsuits are all shredded up so that they're creating all this extra drag. So when they're working out, it's harder to work out. And then when they go to a meet, the night before they go to a meet, they'll shave. And they'll shave usually their chest, their legs, but they won't shave some people won't shave their shins. They definitely won't shave the tops of their feet. And they won't shave the bottoms of their arms, so the bottom sides, because they want the drag to be there still. Not only do they want that drag there, so when they grab the water and pull back, it's a lot of friction that pulls them forward, but they want that feel because it feels different. The flow of the water makes your body feel different in the water. It makes you feel faster, and you are faster. But when you feel faster, there's a psychological impact. And these suits did all of that without shaving, and more. They did even more than that because they created even better flow. It turns out that if you shaved stripes in your body, it would actually be better than shaving everything on your body. But they didn't know that. So the engineers did know that. Swimmers didn't. But engineers did, so they designed their suits so that the water flows in certain places and doesn't flow in other places. It's really interesting the way they did that. Anyway, here they solve that equation for the velocity of a skydiver when their weight equals their drag force. When the gravity pulling down equals the drag force up, that's when the forces cancel to zero and the skydiver is not going to accelerate anymore. And that's when they're going to reach terminal velocity. So they actually solve for the terminal velocity of the skydiver. And you can solve the terminal velocity of anything. Really, there's everything as a terminal velocity, where their forward force, or the force that's propelling them, is equal to the drag force that's stopping them. When those two things are equal, that reaches that. And then you have Stokes' law, which is for an object, a spherical object falling in a really high viscosity fluid. This is Stokes' law. And it usually works for small objects best. Drops of, water, little pieces of dust, whatever. So anyway, and then they have one more equation, which we'll cover next time. We'll finish that next time, then we'll talk more about homework questions, and then we'll have at least Wednesday, a full day Wednesday, to cover any other questions. So work on your homework, work on past homework, get things done as much as possible so we can answer as many questions as possible. Yes, ma'am.
Well, the chapter 6 homework you had gotten to?
I think that we've got, I think we have all of the questions in chapter 6 that we need, except for we might put in a drag force equation or something. I can't remember all the questions that I put in there so far, but let me look really quick. Did we put any friction ones in here? That's friction. That's friction. I might have to put in a turning question, just like a car turning or a plane turning question. But I might put in 2 or 3 more questions, but that'll be it. So, I think we've got just pretty much everything else we need in here. In fact, I'll do that right now before I forget. No, they don't actually have any of those. Not in that one anyway. Might be in this section. Well, it'd certainly be in this section now that I think about it. Actually, now that I think about it, why is that in there? I think this first one doesn't even belong here now that I'm looking at it. Acceleration 2. Looking at number 1 again, trying to figure out why this is actually in this chapter.
Which one?
Number 1. This actually belongs in 2 chapters ago.
Really?
That might work for number one if you want to look over it.
Yeah, I know how to do it. I just don't know why it's in chapter 6. This doesn't have any forces involved, really. So you're trying your question on this one again is so
Well, the second part is confusing.
okay.
Part, part C, I guess.
Okay.
Part C.
So the object is moving at a constant speed around a horizontal circuit right there. At time 1, you have acceleration -3, -5, right? So your vector, your acceleration at let's see, what is our projected time t1 acceleration a1 is -3i, -5k. So -3i. So the circle looks like this. There's a circle for sure. And if your acceleration is -3i, I is this way.
Oh, and
So this is -3i,
this
-3k.
is
Right?
the x-axis, so this is the z, but
Yes.
this is positive. This is negative z. It's not weird.
Okay, it doesn't really matter. It doesn't matter what the.
I want to get the organization right.
Okay, so which one's positive?
This is positive x. This is negative z.
And it's saying you have I, negative I, so negative I is this way. negative k is this way, right?
Yeah.
So that means ours is pointing this way, right? If we have a negative I, negative k vector, ours is pointing this way, somewhere, right? So it's negative 3i, negative 5k, right?
That's acceleration.
That's acceleration. That means it's on this part of the circle. Because it only accelerates on this part of the circle. But wait a
That's on
second.
the acceleration.
Wait, hold on a
inward
second.
is
Constant speed of time 1. So it could either be here or it could be here. Oh, sorry. No, you're right. Sorry. It's not accelerating, it's in constant speed. So, it's constant. So it either has to be, to point towards the center of the circle, it has to be here somewhere, right? So this is negative 3, and this is negative 5, right? Okay, so that's where it is to start. In time 2, it has 5 and negative 3, right? 5i negative 3k. So 5i negative 3k looks like this. It's 5i negative 3k. It's this way, right? So it has to be down here, right?
Right.
This one is 5i negative 3k.
Wait for the first one. That's
This is
negative.
1, this is 2.
So that first one, that's a negative 5. Negative should be up there, right?
Negative, 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 negative.
Yeah, but this is the opposite. See that?
Right, no, it's not where it is, it's where it's pointing. This one is pointing in the negative, negative. So it's pointing that way, so it has to be on this part of the circle. Because that acceleration has to point towards the center of the circle.
Oh.
Right?
Yeah.
So if this is a negative, negative, pointing this way, it has to be here. Can't be here, 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 it has to be here. Right? This one is a positive 5, negative 3. Positive 5, negative 3 has to be pointing this way, which has to be in this quadrant. So it has to go from this quadrant to this quadrant, time 1 to time 2. So time 1, time 1 is 5 seconds, time 2 is 8 seconds. So they want to know what is the period of rotation of the particle if it's moving in the clockwise direction. Okay, so if it's moving in the clockwise direction, essentially we've gone from here all the way around past to here, right?
Wait, what?
If it's moving in the clockwise direction, which is part A, right?
Moving in the clockwise. Oh.
Then it's gone from here all the way around back to here, right?
And that would be a period.
That's one full period plus change. Now, how do we know what the angle is between these two things? Well, you can find the angle between two vectors, but
Oh yeah, I guess you could. But does that outside of the scope of this question, generally? I didn't think about that, but you could.
it's not. You could go back to chapter 1, 2, chapter 2, and figure out the angle between these two vectors. It's essentially you use the sign, or you use the dot product. Is the fastest way to do it.
Dot product over the magnitude. You
Yeah,
get those
the problem with the dot product is you're going to find you're going to get a 0, so you do with the cross product, you get you the right answer. But when the dot product gives you 0, that means that they're 90 degrees to each other.
Right.
So these end up being 90 degrees. So this ends up being 1 period plus a quarter of a period, so 1 1/4 periods. So you have, you've got, so 1 1/4 period is 1.25, each period is 2 pi radians. That becomes 2 pi radians.
Wait, how old should be 1.25?
So this 1 1/4 period. It's 1 period plus a quarter period. 90 degrees is a quarter period.
No.
So 1.25 times 2 pi will tell you how many radians you go through, right? That'll tell you the total radians you go through. And actually, let me do the radians. 1.25 periods and divide that by, divide, how many seconds? 8, time 1 is 5, time 2 is 8. So you take the 3 seconds per period. Sorry, 3 seconds divided by 1.25 periods. And that'll give you seconds per period. It's going to be 2 point something. Wait, that's not right. Well, it's T1. T1 equals 5 seconds. T2 equals 8 seconds. Oh, wait. Oh, no, never mind. They're actually not assuming you went all the way around. They're just assuming you went from here to here, so that's just a quarter of a period. So it's 3 seconds divided by 2.25 periods. So they're assuming they just went this way. They didn't go all the way around. So you just went from here to here, so it's just a quarter of a period. So 3 seconds divided by 2.25. Going all the way around. No, sorry, going counterclockwise, you go 0.75 periods. So you go 3 seconds divided by 0.75. That gives you part B. Then once you know the period, you can go back and calculate. But I still don't think this fits this chapter. I think I'm going to take it out. Is this the only one you're struggling with?
There's some other ones with joints that I haven't got to yet that I'm going to. And also there was the last one.
The last problem?
No, not that one. It was involving.
Oh, I'm
It
sure.
involved some book, and then somebody placed like their book bag down and talking about the static coefficient. And then they're like, select all that is true. I thought I did, but I guess no. Oh, I think that's it.
Looking at a nearby slide appearing on main station, original flying statement is always correct. Bearing the magnitude of the frictional static friction. Okay, so what you have to realize is that you have, if you put it on the slide has some angle, theta, right? Hook here, weight of the hook here, which is equal to mg, right? Then you have the frictional force pushing this way, and of course the frictional force has to be, so the frictional force, so you have this weight in the parallel direction, and the weight in the perpendicular direction, right? The weight in the parallel direction, if this is theta, is equal to mg sine theta. So in order for this book to sit still, the friction force has to be what compared to mg sine theta? It has to be greater. That has to be true. So that's one of the things that has to be true. And it needs to either be greater than or equal to it, right? It has to be greater than or equal to that.
Like with the static friction, they don't have a one that actually says greater than.
No, they don't, but we're not there yet. We're not getting there quite yet. So the force either has to be greater than or equal to that. But remember that the static coefficient, the static friction, varies, it changes. It will react to whatever force is pulling it.
It's matching.
So this is not going to be what? This is not going to be that, it's going to be equal to that. Until it gets to its breaking point. Until this weight, until this part of the weight force is equal to this, or exceeds the maximum that this can reach. Until it breaks through that friction, this is always going to be equal to mg sine theta. So no, because the normal force is equal to this one, right? The normal force is equal to mg sine theta. And let's see what that says there real quick. So, sorry, this one is actually not signed. This one's going to be close. Because this one's next to it. The normal force is equal to this one. The frictional force is equal to this one. The normal force is equal to mg cosine. Not the same as that. So it's not equal to now, the other one,
Did this say this was on a slanted line?
yeah, it says it's on a slide. So then the other one that's always going to be true is if you look through all of these things, these choices you have frictional static equals mu mg. Well, that one's not going to be true because there's the if you have m times g, you're not including the angle in that, right? So mu times mg would be mu times this vector here. So that's way bigger than the frictional static force because we already know that this one is bigger. But actually depends on the angle that you tilt this thing. It's your mu times this mu times mg is actually bigger than mg cosine theta. mg cosine theta is smaller, mu mg is bigger than that. And so it can't be equal to that one if it's not equal to this one. Right? So that's one. The normal force we already know about. Mg cosine theta is the normal force, so we know that one can't be true. And mu times n is it's the static frictional force on a flat surface. And this is a angled surface. So it can't be that one either. Right? So the only one that it can be is the last one. The only one we have to look at is the force of static friction is less than mu times mg. Well, mu times mg is what it is on a horizontal surface. That's what the static frictional force is here. When we tilt this, what happens to that? The mg is the normal force, and the normal force becomes less on a tilted surface. The normal force is maximum when the weight of the book is straight down into the ground. Straight down into the surface, and so the surface can push straight back up. But since this is on a tilted surface, the book pushes down into the surface at an angle, and the surface can only push back at an angle. So part of that weight force pulls the book down, wants to pull it down the side.
So I can see how the mu mass that would be less, or at least the normal force.
The static friction will always be less than
Why is the static friction less than that? That's decreasing, right? Because of
no. What's decreasing is the mg. What's decreasing would be the normal force n. So if you put in mg times cosine theta in there, right? Then you could say that the static friction would be, put in sine theta, put in mg sine theta. You could say, would be mu. Yeah. So if you replace mg here with mg cosine theta, then you could say that those things would be equal. The static friction is equal. The static friction is equal to the mg cosine theta times mu, but it's not equal to mu times mg. It has to have the cosine theta. In fact, frictional static is also equal to mg sine theta. It's equal to this force here. And if you want, you could also take the equivalent of the normal force, which is mg cosine theta, and multiply it by mu, and it would give you the same answer as that. Because that's what the friction does. But I think that I'm going to remove number 1 from this homework assignment because I don't think it belongs here. I don't like it. Don't like it. Don't like it. Don't trash it. So anyway, I have to stop my recording.